Welcome to my chemical process calculations classroom. In this course, particularly in this model, we are discussing about material balance with chemical reactions. That is material balance in unit processes, or you can say material balances in reactive systems. So where at least one chemical reaction is involved in the system. Okay. So here what we should know is there should be balance of atoms. That is, if there are reactants, there are products. When you write a chemical reactions, that should be balanced. How will we say it is stoichiometrically balanced? When the number of atoms in the reactants are equal to the number of atoms in the product. Let me say there are 12 carbon atoms in the reactant, there should be 12 carbon atoms in the product. If there are 24 oxygen atoms in the reactant, there should be 24 oxygen atoms in the product. That stoichiometrically balancing the reaction is first basic thing we should know in writing a chemical reaction. Okay, and in the previous lecture, I hope you have seen watched the previous lecture. In that lecture, what we have discussed, we have defined what are the basics of chemical reaction, what is stoichiometric coefficient, what is stoichiometric reaction, right? We have defined if it is what is single pass conversion, and there is a what is a recycle stream, what is purging, how to determine the yield, what is how to determine the conversion, how to determine percentage excess here, all that, right? So in this lecture, with all this background, we will start solving the numericals in this particular lecture. Okay, ready? Shall we proceed with the problems?
Lecture, we are going to solve some numericals on material balancing unit processes, that is reactive systems. Okay, in the previous lecture, we have seen the definition of stoichiometric coefficient, stoichiometric ratio. So with that, you can do this small numerical. So mostly, you have seen there are different type of reactions. You have given even examples for unit processes like pyrolysis, combustion, alkaline reaction, chloralkali reactions, like that nitration, polymerization, like that various reactions are there. It is time for us to go through all those reactions, and we are supposed to know the reactions. Reactions will not be given. Okay, so we are supposed to know what is the reaction that is taking place. So here we are just starting with the simple reactions. Okay, if it is combustion, mostly what will happen, it will the reactant whatever is given will react with oxygen to form CO2. If hydrogen is present, it will react with oxygen to form steam, H2O. Okay, so that kind of basic reaction we should be able to write. And you know ammonia, what is ammonia? NH3. So you can write down the reaction. Okay, take down this problem number 1. Write down the reaction of nitrogen and hydrogen to form ammonia and determine what are the stoichiometric coefficients of mention the stoichiometric coefficients. For simplicity, I am using here. You write clear fully. Okay. Mention the stoichiometric coefficients of nitrogen, hydrogen, and ammonia. And then second part, what is the stoichiometric ratios of N2 by H2, B, N2 by NH3, and C, H2 by NH3. So for that, first we have to write the reaction, then balance it. Okay, so we have to stoichiometrically balance the reaction. What is the reaction taking place? What are the reactants given? Nitrogen and oxygen. What is the product mentioned? Ammonia. Will there be anything else formed? No. Okay. Okay. So you can balance the reaction now. So that's the first step. First step is always we write the reaction and make it stoichiometrically balanced. When we say stoichiometric balance, number of atoms in the left hand side should be equal to number of atoms in the right hand side. So you will get 3 and 2, right? Is that right? 2 3s are 6 hydrogen, 2 nitrogen, 2 3s are 6 hydrogen. And okay. So once it is stoichiometrically balanced, so we know it is here that 1. Okay. So what is the answer for first part? Mention the stoichiometric coefficients of nitrogen, hydrogen, and ammonia respectively. What are they? You can write the answer as the stoichiometric coefficients of nitrogen, hydrogen, and ammonia are 1, 3, and 2 respectively. Okay, that is the answer for this part. The next part is what is find out the ratios, stoichiometric ratios. What is the ratio in which nitrogen and hydrogen are present in this system here? So what is the stoichiometric ratio? Number of, so write the formula here. What is the definition of stoichiometric ratio? Stoichiometric ratio of nitrogen by stoichiometric ratio of hydrogen is equal to stoichiometric coefficient of nitrogen by stoichiometric coefficient of hydrogen. So here we have already written what is the stoichiometric coefficient, right? The stoichiometric coefficient of this one is 1, by hydrogen is 3. So answer is 1 by 3. Similarly, for we can complete the second this part and this part. For nitrogen by ammonia it is 3 by 2. So it can be written for ratio for within reactant, or it can be written with product and reactant also, or reactant and product also. So hydrogen by ammonia is 3 by 2. What is nitrogen by ammonia? So this
1
is
by 2 kg.
okay. So for nitrogen, this one nitrogen is 1 by ammonia is 2. Hydrogen by ammonia is 3 by 2. So that way you can write down what is stoichiometric coefficient and what is stoichiometric ratios. Okay. So that I think if you have watched the lecture, there should not be any doubt in that. I will do one more numerical involving a reaction. See, with respect to chemical reactions, we have there, say for example, let us consider this simple reaction. C is forming CO2, so it may be C plus O2 be forming CO2. So if there are X, so we have seen the stoichiometric coefficient, right? Here it is 1, 1, 1. Always we should know to write that it is actually what is that? If it is in kg moles, 1 kg mole of C reacts with 1 kg mole of oxygen to form 1 kg mole of CO2. Okay, so if I multiply by the respective, in terms of mass, how I can write the same? We should multiply by the respective molecular weight. 1 into 12 kg per kg mole gets cancelled. So we get 12 kg of carbon reacts with this O2, right? So 1 into 32 kg of oxygen. CO2 how much? 36 plus 12, 48. 32 to 44, right? 32 plus 4, 44. So we have 44 kg of CO2. What is that? If you want to convert it, multiply by respective molecular weights. Okay, so with respect to this material balance in chemical reactive system, our first step will be to, again, as usual, we have to form a basis. Mostly we have seen that it will be mole basis. Okay, in terms of kg moles or pound moles, we will be considering. Okay, even if data is required in kg, we have to multiply, convert it finally into kg. Okay, so we will consider mostly mole basis in the system. Okay, the second point we should know is we have to calculate the molecular weights of all the components. Okay, even if it is not asked what is the molecular weight, we have to show what is the molecular weight of each component. Let us list it. Whatever is reactant involved, we have tried that. Okay, if it is inert, we need not write it. Okay, if it is inert, we don't know what is that inert. Sometimes if it is mentioned inert is methane, it's not taking part it, we can even write the molecular weight of that material. But if it is simply mentioned as inert, we need not find the molecular weight for that substance. Okay, and then we have to first consider how much kg mole. We see, let us consider 10 kg mole as the basis. Okay, if we have 10 kg mole of C is there, let me say 100. Let me say 100 kg mole of C is there. So what is the reaction taking place? We have seen 1 kg mole C will react with 1 kg mole of oxygen to form 1 kg mole of CO2. Right? So how much kg mole of CO2 will be formed? It will form 100 kg mole of CO2. Okay, when I say like this, I am actually making one assumption here. What is that intrinsic assumption here? I am making an assumption that this 100% conversion taking place. What I am saying is there are 100 students in the class. 100 students have passed in the exam. So what we are making assumption that everybody studies well, right? Like that. Here the conversion pass percentage is 100%. Then only we can say 100 people have passed in the exam, right? Same this here. When I say 100 kg mole C, we are making an intrinsic assumption that it is 100% conversion. But usually, because the reaction taking place is also depending upon various parameters like temperature, pressure, purity, okay, or even you can say that presence of purity. When I say presence of foreign materials, okay, depending upon if it is a catalytic reaction, it may be a catalytic activity, okay, effectiveness of the catalyst, efficiency of the catalyst, right? So catalytic activity. So like that, this conversion may not be 100%. So it may vary from 0 to 100%. Okay, so that way there is a probability that the conversion may be less than 100%. Okay, when I say 100% conversion, what is how we are defining conversion? Number of kg moles initially 0. Okay, 100 kg mole of C. In the product there is 0 kg mole of C. So conversion is initially 100 was there, finally only 0 is there. Okay, so what we get is 100% conversion, right? So, but there is a probability that due to various reasons the conversion may not be 100%. Okay, in that case, so the conversion will not be 100%. So let me say in the same, if I consider a case here, 100 kg mole of carbon is there, and in the problem in statement it is mentioned that, or if we ourselves know that this reaction is only 80% conversion is possible. Let me say 80% conversion takes place. Question is, there is 100 kg mole of C and there is 80% conversion. How much kg mole of CO2 will be formed? So in that case, even though in the feed there is 100 kg mole of C, okay, in the feed we have 100 kg mole, but out of that, what is the conversion given? Only 80% is taking part in the reaction. Okay, so let us make it clear here. If it is a reactor system, you have 100 kg mole A is entering. How much kg mole of product C? Let me say A plus B gives C. So in this case, it is C plus O2 giving CO2. We are giving, assuming it can be for any reaction. Okay. So if it is 100% conversion, how much you will get? We will get 100 kg mole of C. If it is 50% conversion, so what does that mean? The product not only contains kg mole, so we will have pure kg mole if it is 100% conversion, right? But if it is not 100% conversion, for 100 kg mole of A, product will contain this much kg mole of product, also unreacted C, A. Okay. If A is also there, this much kg mole of A will be there. What is that? It is unreacted A. Okay, so how to know how much kg moles is present? If it is 50% conversion, so out of 100, only 50% is taking part in the reaction, right? So amount of CO2 formed is out of 100, only 50%. That is 50 kg mole will take part in the reaction, right? So out of 100 kg mole, if the conversion given, whatever is the conversion, if it is X, it is X percentage. Okay. So yeah, this X by X percentage is given. Like it may be given like 25% or 95%. Okay. There may be some process where we may have 99%. Okay. So that will be X, whatever is the value X percentage, it is X by 100 into 100. Whatever is the basic feed basis you have taken, 100 kg moles, only that much is taking part in the reaction. And we have tried the reaction that 1 kg mole of A reacts with 1 kg mole of B to form 1 kg mole of C. So what is happening? So 1 kg mole of A reacts with 1 kg mole of B to form 1 kg mole of C. So in this only 50 kg mole is taking part in the reaction. So you have to multiply by 50 throughout, because here whatever the ratio you will get, right. So 50 kg moles of A will react with 50 kg moles of B to form 50 kg moles of C. So here C is equal to 50, and out of 100, 50 is taking part in the reaction. So what is the amount of A present in the product then? 50, right? So here it is not unit operation, it is unit process. Okay, so it is a reactor. When the combustion is taking place, it can call it as combustor. Okay, combustion taking place. Or if it is pyrolysis, you can say pyrolysis. So that conversion factor we should know. But if it is not mentioned, what we are assuming? We are assuming the conversion to be. So this thing we should know. Okay, or better we assume that one. You explicitly write it down that here conversion is not mentioned. It is simple problem to start with. It is not mentioned. But if there is later stage, we are going to consider different conversion only. But whenever conversion is not given, we have the liberty to say that it is 100% conversion. Okay, that is one thing we should know. Another point we should know is the feed is, even though A, what will say, it will be say that we have 100 kg mole of feed. Okay, but it may be mentioned that the feed contains only 80% A and inert is 20%. So let us say in the same case, there is 100 kg mole of feed with 80 percentage A and inert is 20%. Let me say that A is same reaction. Let us consider C plus O2 giving CO2. Okay, so if the same reaction, if data is given like this, 100% kg mole of feed is there, which contains 80 percentage of A and remaining inert is 20%. The inert here refers to, it may be another product also. Okay, whatever. Here A is 80%. So out of this 100 kg mole, what is the composition? We have A is 80 by 100 into 100 kg mole, which is equal to 80 kg mole. Okay, and inert is 20 percentage of 100, which is 20 kg mole. Okay, so in this only 80 kg mole is available for us A. Now in this we can have two cases. In this, if it is given 100, no percentage conversion is mentioned, we can assume it to be 100% conversion. Okay, so we can have two cases. If it is 100% conversion, another case 50% conversion. So what is the amount of CO2 formed? Here we have to always write this thing. Okay, that what is that? 1 kg mole of C reacts with 1 kg mole of oxygen to form 1 kg mole of CO2. Okay, so here what is, if it is 100% conversion, what is the amount of A reacted? 80 kg mole. Okay, if it is 50% conversion, A reacted is equal to, out of 80, only 40 kg mole is reacting. So what is the kg mole of CO2 formed for first case and A case and B case? So from this, multiply by 80 throughout. So what is that? What you get? We have 80 kg mole of C reacts with 80 kg mole of oxygen to form. See, remember, we are considering a simple case of 1 is to 1 is to 1 ratio. Without writing all this also you can do. But what in general, well, let me say, for if it is a general reaction, it can be AA plus BB giving some product PP. Okay, so then in that case, you are going to have A, B, C, P here, right? So that way it can change. Here it is simple because we are considering a simple example of combustion of coal, C plus O2 giving CO2. Okay, so we have 80 kg mole of carbon giving 80 kg mole of oxygen giving 80, sorry, reacts with 80 kg mole of oxygen to form 80 kg mole of CO2. That is the case for answer for when it is 100% conversion. Similarly, if it is 50% conversion, amount of A reacted is 40 kg mole. So for B, what is the answer? Multiply this equation only. Okay, multiply by 40 throughout because it is 40 kg mole. So 1 kg mole, 1 kg mole, 1 kg mole. So you are going to get all are 40 kg mole of carbon reacts with 40 kg mole of oxygen to form 40 kg mole of CO2. Okay. So this is one case. This is one case, right? So if the conversion is 100% and conversion is not 100%, this can have difference. So this can be done for different percentage of conversion. Okay, that is one thing. Now, if it is asked, what is your question is what? How much kg mole of CO2 is formed? Okay, how much kg mole of CO2 is formed is the question, means we can leave here. Okay, but if it is asked, how much kg of CO2 is formed? How much kg of CO2 is formed? What we have to do? Here, in the case, what we will be doing is multiplying by the respective molecular weights. Carbon molecular weight is 80 into 12 kg mole of carbon, 80 into 32 kg mole of kg mole. When you multiply by kg, 12 is kg per kg mole, so that kg mole gets cancelled. So what I have is kg. Okay, so we get kg of carbon, this much kg of oxygen, equal to 80 into 44, 32 plus 5, 44 kg per kg mole. So we get this much kg of CO2 form. Here also same, so 40 into 12 kg of carbon reacts with 40 into molecular weight kg of oxygen equal to 40 into molecular weight kg of CO2 will be formed. Okay, so this is one way this can be done if data is directly given. There is one reaction taking place. Okay, there is probability that there are more than one reaction taking place. Let me say that it is given same problem. It is given that C plus CO2 is formation is there, and if it is incomplete combustion, we will have carbon monoxide formation, right? So, so if it is given like this, and it is given that there are 100 kg mole of A, if it is given there are 100 kg mole of A, in that 80% reaction, 80% conversion, we will say 80% CO2 is formed and 20% CO is formed. So in that case, we have to consider both reactions. Okay. So how to proceed? So we have 100 kg mole of A. Let us say it is pure. There is no inert. Okay, inert is 0. So we can take a basis of 100 kg mole of A. Okay, we can take a basis of 100 kg mole of A, and what does it mean? It means it has 100 kg mole of A, nothing to do. It says that 80% of A is consumed towards carbon is A is consumed for reaction 1, reaction 2. Let me say reaction 1, let me say reaction 2, then it is mentioned that it is 80% is converted to CO2, 20% of A is, remember, 80% of A forms CO2, 20% of A forms CO. So that is the given information. So what is happening? So in this case, we have to consider our basis is 100 kg mole, and we have tried the reactions, right? So first reaction, according to first reaction, it is 1 kg mole of C reacts with 1 kg mole of oxygen to form 1 kg mole of CO2. Okay, so another case, reaction 2, 1 kg mole of carbon reacts with 0.5 kg mole of oxygen to form 1 kg mole of carbon monoxide. Okay, so what does it? So we have 100 kg mole. In this, 80% takes part in first reaction. Therefore, 80 kg mole will go here, right? Means 80 kg mole will be taking part in first reaction, and we have 20% of A taking part in second reaction, which is 20 kg moles. Okay, so first reaction we have 80 kg moles taking place in the reaction, taking part in the reaction. So what is happening here? Again, here also we are assuming 100% conversion means out of this 80 available, 80 kg mole of carbon reacts with 80 kg mole of oxygen to form 80 kg mole of CO2. Here what is that happening? 20 kg mole of carbon reacts with 10 kg mole of oxygen to form 20 kg mole of CO. Okay. Here I can define one more thing what is required also. So this is what happening. So out of this 80 kg mole of CO2, the product formed is 80 kg mole of CO2 and 20 kg mole of CO. We can multiply by the molecular weight to know how much kg of CO2 is formed, how much kg of CO is formed. You can complete that. Please complete. 80 into 44. Here 20 into carbon monoxide. 16 plus 12, 28. Okay. So what is the answer? One of you unmute and answer.
3520, sir.
For CO2?
Yes, sir.
CO2? 3520
20.
kg of CO2 is formed. Here?
560.
5?
60.
Okay. Just for confirmation, what is this value? We have 100 kg mole of A. 100 kg mole of carbon. How much kg carbon it is?
1200.
1200.
Okay. Let us calculate what is the oxygen requirement. So just to see, remember mass balance should be same. For that purpose, I want to know. Here we have defined one more term called theoretical oxygen demand. Theoretical oxygen demand. You can say TOD. Theoretically, how much oxygen is required? You can say oxygen requirement. Okay. So theoretical oxygen requirement is equal to theoretically as per stoichiometric reaction, how much kg mole of oxygen is required. So oxygen required for reaction 1 plus oxygen required for reaction 2, right? So here how much oxygen is required? 80 kg moles plus here 10 kg moles. How much total? 90 kg moles of oxygen is required. So tell me how much kg of oxygen is required then? TOD.
1440.
How much?
2880.
2880, yes.
2880.
So we have 2880 kg of oxygen is the theoretical oxygen requirement. Okay. Now, why I am doing this kg basis is we are talking about what we are doing is material balancing in a reactive system. No? So let us say total feed in terms of mass it should be equal. In terms of kg mole it won't be equal, but in terms of mass, what is total feed? What is the total feed and what is the product? So let me say in feed is C, oxygen, right? CO2, CO. In the feed, is there any CO2? No. Is there any CO in here? No. Okay. Let us make a mass balance here. In terms of kg, how much kg is carbon? We have calculated, right? 1200 kg. Got it? We have 1200 kg of carbon. And how much our oxygen we have? 2880. How much is, what is our product? 3520 CO2 and 560 CO. Make a total. So remember, usually there will be, when I say oxygen, we will be sending some nitrogen along with it. Whatever is nitrogen is entering, the same amount will be present in the product also. In that case, it is called a flue gas analysis that I am going to discuss in next problem. So here right now, we are not concerned about nitrogen. We assumed only oxygen is entering the system. But actually, we will not sending oxygen. We will send air. So proportionally, in mass mole basis, we know 7921, or in mass basis, 2377. So 77 into 23 ratio, you will have nitrogen, oxygen in the air. So that can be added again. So right now you do the material balance here. What is in terms of kg? Make a total. What is the total here? 0.
4080.
4080.
80.
Here what is the zero value? 40.
Same.
So that is what our calculations are correct. This is called verification. Okay, so how to verify the material balance for reactive system? The concept, important point to know is mass balance should be same. Mass in terms of kg, total kg entering the system is equal to total kg leaving the system. Okay, so that should be justified. That should be verified also, because whatever calculation we did so far, if this is not matching, it means somewhere we did calculation mistake. Okay, so that way, so we should know that kg moles will not be equal. Okay, kg moles of input will not be equal to total kg moles of output, but there will be kg of input will be equal to kg of output. Okay, so that then only our calculation is correct. Okay, so these are general points which I just took a simple general case and try to explain you. So all this what we are going to do. Okay, okay. One more thing also can be explained here. So what we have determined is theoretical oxygen demand. Okay, what we have determined is stoichiometrically we want this much kg of oxygen. But what usually what happens, no, we will not have the required conversion taking place if you only supply oxygen in the same ratio. So it is like now there are 10 boys, there are 10 girls, and we expect them to get married. Okay, so what happens is some may not be compatible, they will not get into the relationship, right? So that way it is not, it is always better if you have more choices. Okay, let me say if I send 100% extra, then probability that these 10 girls will choose one out of two, and there is a probability that they get into a relationship, right? So like that, so always it is excess oxygen is supplied. Okay, to ensure the required reaction is taking place. Okay, why not it is taking place? Because that whatever is the oxygen available, there may be leakage. That oxygen, some other reaction, side reaction may be taking place. Like that, due to various reasons, that if you are sending in only theoretical required oxygen, we don't get the reaction that is effectively taking place. Okay, so that way, always excess oxygen is supplied. So in that case, there is let me say theoretically we want 2880 kg only. Okay, so what is probability is there is always 100% excess is supplied. Okay, so you have theoretical oxygen demand and actual. So in that case, what we call is actual oxygen supplied. Okay, there is theoretical oxygen demand. This is actual oxygen demand. What is actual oxygen is percent depending upon how much percent we are sending in excess. Let me say we want 100 kg mole of oxygen, but I am sending in 200 kg mole of oxygen into the system. So what does it mean? I am sending 2 times more the theoretical oxygen demand. Okay, so that is 100% excess oxygen is supplied. Okay, what if I say that is 200% excess oxygen is supplied? It is 300 kg. That is one is theoretical oxygen demand plus 200 demand. 100 is 1 times plus 200 times, right? So totally we will be sending 300 kg mole of oxygen is supplied to the system. So remember here in terms of kg mole 90. What we theoretically required is 90 kg mole in this example. But if I am sending 180 kg mole of oxygen into the system, what does it mean? We are sending 100% excess oxygen. For the same problem, if I say 50% excess oxygen is sent, then what is that? 1 plus 50%, 0.5 into theoretical oxygen demand. So actual oxygen demand is equal to 1 plus whatever is the percentage fraction is given. Okay, one is actual theoretical demand oxygen plus excess is 0.5 excess. Okay, that is 1.5 times TOD. That is 1.5 into, in this problem it was 90 kg moles of oxygen. That is 1.5 into 90. What is that? Half of it, 90, 45. So 90 plus 45 is
135.
the value. How much?
135. 35.
135 kg mole of oxygen is supplied to the system. Understood? So if I give 100%, what is that? Instead of fraction, in terms of fraction, what do you say? Let me say it is X percentage excess. Then it is 1 plus X. Not X by 100 actually, right? So we can say if X% excess air is sent, then actual oxygen demand is 1 plus X by 100 into theoretical oxygen demand. See, remember this can be calculated in terms of oxygen or in terms of air. Why in terms of, if it is oxygen, what will happen? For every 21 kg mole of oxygen, nitrogen content will be 79 kg mole of nitrogen, right? So total is for 100 kg mole of air, for every 100 kg mole of air, make your attention here, for every 100 kg mole of air, there will be 21 kg mole of oxygen and 79 kg mole of nitrogen, right? So now, whatever is your oxygen, if I say excess in terms of oxygen, proportionally it means excess in terms of air. So there should not be confusion for you. Sir, air is given excess air, because if I say oxygen, excess oxygen, then okay. Or even if it is mentioned excess air, that also it means the same. Okay, because there is a particular fraction ratio. If oxygen is 50% excess, proportionally nitrogen is 50% excess. Therefore, proportionally air is also 50% excess. So in the question, you should not get confused. If it is mentioned, either it is excess air or excess oxygen is supplied. Okay, so we should be able to calculate the percentage excess of air. Or I can simply tell, with this problem itself, I will tell you. Yeah, for a combustion reaction, theoretical oxygen demand is 90 kg mole. For a reaction, theoretical oxygen demand is 90 kg mole. but actual oxygen supplied is 135 kg moles. What is the percentage excess of oxygen supplied? Okay, how much percentage excess is supplied can be calculated, which we should get 50% because we calculated here already with reverse one, right? If it is 50% excess, we calculated it to be 135 kg moles, right? So you should be able to write a general formula how to get what is the percentage excess oxygen supplied. So how it will be? Check it. 135 minus 90 divided by 90 into 100, right? So what you get is 45 by 90 into 100, which is 50%. So what is the formula for percentage excess for oxygen? Percentage excess oxygen can be determined by actual oxygen supplied minus theoretical oxygen required by theoretical oxygen required into 100. Okay. So that can be determined. Any doubts so far? One of you unmute.
Yes, sir.
Okay. Now we will do a problem. Simple problem will do.
And conversion.
We take down this problem. So remember, we are not going into recycle single pass conversion, overall conversion right now. That I will do it in next lecture. So now what we are doing is simple material balance in reactive system. We should be thorough with this. What is stoichiometric coefficient? What is stoichiometric ratio? What is theoretical oxygen demand? What is actual oxygen or theoretical? What is the? We should be able to determine what is the air requirement, theoretical air requirement. What is the actual air requirement? Okay, then percentage of excess oxygen, what percentage excess air, all that. Okay. So even this problem, you can complete that part also. If 90 kg actual air, okay, we will not get into the excess part. If 90 kg mole is the oxygen required, what is the air requirement? Theoretical air requirement. Theoretical air requirement is equal to. So we know that 100 kg mole of air contains 21 kg mole of oxygen, right? So 100 contains 21, but what we have is 90. So what is the air requirement? So it is 100 into 90 by 21. So what is the kg mole of air required here? One of you unmute and answer. 100 into 90 divided by 21. 428.57. Is that right?
Yes, sir.
428.57. You can round it, no problem. Rough calculation. So 429, almost 429 kg moles is air is required. Out of this 429, how much is nitrogen? Theoretical nitrogen is equal to, so out of this 428.57, 90 is oxygen. So the rest is equal to nitrogen, right? Minus, this is 338.57. Is that right? 97.
Yes, sir. Right.
So this is theoretical air. So what we can say is the air is 428.57. Out of that, oxygen and nitrogen are, oxygen is 90, nitrogen is 338.57. Okay, so this is our theoretical part. Okay, so what you can do is actual, whatever is actual can be determined depending upon what is the percentage excess. Okay, numericals can be asked in forward direction or reverse direction. Okay, you may be given what is the actual air supplied and determine percentage excess, or directly percentage excess is given. So what is the actual air required can be determined. Okay, so what is the actual air composition can be again written if we know the what is the percentage excess. Okay, so these things we will be using all these in this problem. Take down. In the combustion of heptane C7 14 plus 2 16. In the combustion of heptane, CO2 is formed assume that you want to produce 500 kg of dry ice per hour. Okay, and that 50 percentage of CO2 can be converted into dry ice as shown in figure. How many kg of heptane must be burned per hour is the question. What is that? There are two inputs. One is heptane C7, it's 16. There is oxygen required. No? Combustion means we have to do. So we have a reactor, and there is other products being formed. This is a diagram given in the question. Okay, and there is CO2 gas leaving the system, which is given as 50%, and only 50% of CO2 is converted into dry ice. Okay. Dry ice is nothing but CO2. Okay, so that is again 50%. Okay, so the CO2 in the solid form, CO2 in the gas form. That is what happening. So let me say there are 100 kg moles of CO2 form. In that case, only 50 kg mole is going into CO2 and 50 kg mole is going into dry ice. Okay, remember with respect to reaction, we have to tell. So that is the question.
Sir, here gas 50% and dry ice 50%, or out of 50% CO2 form, another 50% is converted to dry ice.
Both. What is the meaning? That's what I told with example. If 100 kg mole of CO2 is formed, out of that 50% is going as gas. Okay, and 50% is going as ice.
So here
So
efficiency
here,
is 100%, right, sir?
Yeah, we are intrinsically we are assuming that. That's what I told you. It is not mentioned. We are assuming it to be 100%.
sir, here we can say that dry ice conversion rate is 50%, right? Because directly we can apply that.
Yeah. So that's what. First you write the reaction. What is how? First heptane plus oxygen giving CO2 for plus water. You have to write. What is the reaction taking place? Let us write. I'll explain. So if you understood, you can proceed with the reaction. If you know the reaction, you can go. So others can follow. Okay. So the data given, I will write. So to solve it, what we have to do? We have to take a basis, and it is given to produce 500 kg of dry ice. Okay. That is 500 kg per hour. It is given, right? So let me say 500 kg. 1 hour basis, if I take, it is 500 kg of dry ice is formed. So what is heptane C7? H16. What is that? Combustion is taking place. What are the products formed? CO2 plus water. Remember, whenever any hydrocarbon is burned, you are going to have CO2 plus H2O in general formula. Okay, whatever is X, you can even remember that what will be the coefficients. Okay, write the stoichiometric coefficients. Okay. So balance it. How much with respect to which is minimum presence, that you can make a balance. Hydrogen is present minimum, so we can start with that, right? Hydrogen is 16 in atoms here. Here means it should be 8. Okay, so there are, now you can go with carbon also. So there is 7 carbon in the left hand side. There will be 7 here. So now you do the checkup for oxygen to write with the right hand side how much. Here 14 plus 8. Okay, how much?
11.
11.
11 to 22. Total should be 21 oxygen atoms. The right hand side. So now this is the first step. So without knowing this, we can there is nothing will be correct if we proceed without learning to do how to do the stoichiometric balance. Okay. Even if we don't know, you remember for any hydrocarbon, if it is combusted, two products are CO2 and water. First do the balance for minimum, whichever is minimum present. That is one place, that balance you can do start with. So there is 7 carbon atoms. So I put 7 here. For hydrogen, present at one place. So 16 is there. 8 2s are 16. Then it should be automatically adjusted. So 14 plus 8, 22. So 22 by 2, 11 oxygen atoms are required. Okay. So first you write the molecular weights of all these things. As I said, what you will do? Second step is determine the molecular weights. What is the molecular weight of C7H16? 7 into 12 plus 16 into 1, 2 G per kg moles. Okay. What is the molecular weight of CO2? 44. Yeah, what is the molecular weight of heptane?
100, sir.
Okay. With one digit construction, we will get 100. Okay. So this we have. So what we should know is, as you already we discussed, for 1 kg, for 1 kg of, in terms of mass, for 1 kg of CO2 form, ice formed can be 0.5 kg. Okay. There is only 50% of CO2 is used to form dry kg of dry ice. Okay. So here the question is to form 500 kg of dry ice. To form 500 kg of dry ice, we should know how much kg of CO2 should be formed. So it should be 1000, right? You can calculate it with 500 into 1 divided by 0.5, which is equal to how much? 1000, right?
Yes, sir.
Yes, sir.
So we should know that there should be 1000 kg of CO2 formation. Okay. But we know, but what is the reaction we have in terms of kg mole, right? So you can find that again. Let me write here. Reaction is what is that? What is the stoichiometric equation here? 1. So I can write. So actually we should follow it by the reaction. We have to write this. 1 kg mole of C7H16 will react with 11 kg mole of oxygen to form 7 kg mole of CO2 plus 8 kg mole of. So I am writing in detail so that in your mind you know to transform this reaction into kg moles and kg. Okay. 8 kg mole of water is formed. Okay. What we have to do next? We have to write multiply by the respective molecular weights, right? If you want in terms of kg mole. right? Or you can do two ways you can do. Here what we want is 1000 kg of CO2. So that is equal to how much kg moles of CO2 you want to form. I'll do it in another way. Okay. So what to do? We have to, if we multiply by kg per kg mole, it won't get cancelled. So you have to divide by molecular weight, right? So what happens if we divide by molecular weight? 1000 kg of CO2 is equal to 1000 divided by 44 kg per kg mole. So this kg gets cancelled. We get 1000 by 44. How much?
22.72.
22.727 kg moles of CO2 has to be formed. Okay, so now we know there should be, what is the, in as per stoichiometric balance, for 1 is to, you can simply ratio. I see, if I know this clearly, I can even write 1 is to 11 is to 7 is to 8. What are they? It is that product A, reactant A, oxygen, CO2, and water. Like this also we can proceed, but to understand the things clearly, we should write in detail. Okay, because somebody looking at this should know what is this. Okay, so that's why we are writing the same in this fashion. Okay, so 1 kg mole of heptane, 11 kg mole of oxygen, 7 kg mole of CO2 is the ratio in which they are reacted, or in the ratio which is formed. So how much we want to get to form? 22.727. So you can follow that. So what is the question? First, according to question, we will do. Question is, how many kg of heptane must be burnt per hour? In this question, there is no oxygen demand question, right? The only question is how much kg is burnt. Okay, so how much kg of heptane must be burnt? So we can find out that. So what is that? 1 kg mole of heptane will form 7 kg mole of CO2. Okay, so then to form 22.727 kg mole of CO2, how much kg mole of heptane is required? You can find that 1 into 22.727 divided by 7. This much kg moles. How much?
3.25.
What we get is 3.25 kg moles of, right? So we have, now question is asked in mass, right? Question is, how many kg of heptane must be burnt per hour, right? So you can multiply by molecular weight of heptane. Multiply or divide? Yeah, multiply. Multiply by molecular weight of heptane, 100.1, right? Or 101? 100 kg per kg mole. So we can get answer in terms of kg. So what is that? It's 3.25, or you got something like, you rounded it to 2 digits, right? Okay.
Yes, sir.
Okay, multiply by 100 means you are going to get 325.1 kg of C7. That's 16. Okay. So write the answer in the sentence as asked in the question. How many kg of heptane must be burnt per hour? Hence, 3251.1 kg of heptane must be burnt to form 500 kg of dry ice per hour. Okay. I repeat. So what we have question, what is given in the question is To produce 500 kg of dry ice, what must be the kg of heptane that should be used? So heptane is entering, oxygen is entering. So we have, and it is given that only 50% of CO2 can be converted into dry ice. So what we want is 500 kg of dry ice. First we converted that 500 kg of dry ice. To get 500 kg of dry ice, we want 1000 kg of CO2 should be formed, and we converted that 1000 kg of CO2 into kg moles. 1000 kg as 22.727 kg moles of oxygen. So we got converted the amount of carbon dioxide to be formed is as 22.727 kg mole of CO2. Now, and we wrote the reaction. What is the ratio in which they are taking part in the reaction? 1:11 of heptane and oxygen will form 7:8 ratio, carbon dioxide and water. Okay, so it is as per stoichiometric ratio. To form 7 kg mole of CO2, we want 1 kg mole of heptane. And to produce this 22.727 kg mole of CO2, how much kg mole of heptane has to be formed is calculated, which comes to be 3.25 kg mole of heptane. But the question is asked in terms of mass, in terms of kg. So that is, we have to multiply by the molecular weight. Kg mole get cancelled, and we get 325.1 kg of this the product. Hence, we have 325.1 kg of heptane must be burned to form 500 kg of dry ice per hour. So that is our answer. Okay, I think it is across the time. Okay, in this lecture, what we have seen is, first we have seen what is stoichiometric coefficient, stoichiometric ratio, how to solve a numerical to find out what is the stoichiometric ratios, right? So then we have seen what is the theoretical oxygen demand, actual oxygen requirement, what is percentage excess here, like that. And we did one numerical to find out the requirement of raw material based on particular mass of product requirement. So that is what we have to do. And also in this particular main thing to note is, in terms of mole, whatever is entering the system, total moles entering may not be equal to total moles leaving. But with respect to mass, even though it is reactive system, total amount of mass that is entering into the system will be equal to the total amount of mass leaving the system. That's what we have verified also in the one of the numericals. Okay. I think we will stop this lecture here. In next lecture, we will go to the next level where we will look into this recycle, purging, all that. Okay. We will do some more example problems to calculate the raw material requirement, percentage excess requirement. The main that is coming under the combustion reactions. Okay. So if you look at combustion reaction, we will be mainly dealing with the determination of theoretical oxygen requirement, actual air used, like that. Okay. Then we will proceed to some other reactions where we will look into this percentage conversion. So next few lectures more important with respect to chemical engineering, because next semester you are going to have a course called chemical reaction engineering, where we will mainly read about what are the reactions, what is order of the reaction, what is percentage conversion, all that, what is the rate equation, how to determine the percentage, all this. So here what we are doing is material balance for chemical reaction.
In this lecture, we have solved some numericals on how to write out the stoichiometric ratios for a given reaction. So then we have solved a numerical to determine what would be the amount of reactant that would be required to form some 500 kg of dry ice, right? So in that we have first written down the chemical reactions, then wrote the kg mole balance, then converted them to mass balance. Then we have even verified that what is the total amount of mass entering and what is the total amount of mass leaving the system. And we have done another numerical also, in which we have considered heptane, N-heptane, and how much N-heptane would be required these things to get a required amount of product. Okay, so all this involves material balance in chemical reactions. So these are simple problems. So once we are thorough with this the basic simple problems, we should be able to do some more complex problems. Okay, so in the next lecture we will discuss about more complex problems. Okay.